Welcome to this explainer. For decades, engineering has been absolutely laser-focused on building functional artifacts. We make sure the bridge holds weight, the software actually compiles, the engine runs smoothly. But today, we're tackling a fundamental shift in how we approach the world's toughest challenges. Because, well, just building things that work in isolation, it's simply no longer enough. We're moving away from that old paradigm and shifting towards solving deeply complex problems in dynamic, incredibly unpredictable spaces. And to pull that off, we need a bit of a superpower. We need systems thinking. So this brings us to a massive and honestly kind of uncomfortable question. Why do technically perfect systems still fail? Traditional engineering is incredibly hard right out of the gate. Getting the math right, aligning the architecture, hitting all those specs, it's a monumental task. But the central conflict we're facing today is that even a flawlessly built, technically perfect solution can just completely fall apart when it hits the real world. Why is that? Well, it's because the failure doesn't always come from some technical inadequacy. A lot of the time, it comes from an inadequate appreciation of the actual situation. And that messy situation is exactly what pioneers like Riddle and Weber called wicked problems. In a wicked problem, just trying to formulate the issue is tough. You've got different stakeholders who completely disagree on what the actual problem even is. And here's the real kicker. The second you introduce a proposed solution, you fundamentally change the situation itself. It's wild. We aren't just solving fixed, nicely bounded requirements out of a textbook anymore. We are actively intervening in shifting problem spaces that are constantly being molded by politics, the environment, and human behavior. So we're really facing a dual challenge here. On the one hand, we've got the complexity of the system, right? The architecture, the interfaces, the technical validation. And let's be real, systems engineering has always been great at this. But on the flip side, we have the complexity of the problem space. We're talking about the stakeholders, the governance, the constantly evolving environment. What we really need here is a yes and approach. Yes, validating the system requirements is absolutely crucial, and we must also validate the entire situation surrounding it. You literally can't succeed by only looking at one side of the equation. When you map this all out, you start to see the system being engineered. The requirements, the design, the integration, but it's operating inside a much larger, incredibly messy problem space, filled with diverse values, institutions, and rapid change. And right there in the center, acting as the bridge, is systems thinking. It connects those isolated, local technical decisions to the wider, real-world outcomes. Because if you only look at the engineered system, you run the risk of building a solution that's technically brilliant, but systemically useless. Systems thinking is the tool that helps us make sense of this whole map, making sure we don't prematurely lock into a solution before we truly understand the problem space. Let's look at how this plays out in the reality of our modern, super interdependent world. Because engineered systems are almost never standalone anymore. Today, a single platform relies on sprawling software networks, highly complex global supply chains, strict regulations, completely unpredictable human operators, and pressing environmental constraints. It's overwhelming, right? A tiny efficiency gain in one of these areas can easily trigger a massive system-level fragility in another. You just can't evaluate engineering choices solely at the component level anymore. It simply doesn't work. This crazy level of interdependence usually results in what we call systems of systems. Basically, these are independent systems interacting to produce outcomes that no single system could ever deliver on its own. Think about smart cities, or sprawling healthcare infrastructures, or disaster response networks. The constituent parts, like the ambulances, the traffic lights, the hospital databases, they all have different owners and completely different life cycles. So integrating them isn't just some technical challenge. It relies hugely on governance, organizational alignment, and intense stakeholder negotiation, simply because no single engineer has full control over the whole setup. Which brings us right to the human element, stakeholder diversity. As inspired by Checklin's work, we have to realize that different actors hold entirely different worldviews on what improvement even looks like. A system that looks incredibly efficient to, say, a chief financial officer might look like a total nightmare to the maintenance crew actually working on the ground. For instance, if you optimize a design solely to lower the initial acquisition cost just to keep the finance team happy, you might end up drastically jacking up the through-life maintenance costs for the operators. Needs and requirements aren't just pure technical inputs, they're heavily shaped by context, ongoing negotiation, and completely different sets of values. Because all of these moving parts, the technology, the people, the environment, are constantly interacting, we arrive at what is really the climax of systems thinking, emergence. Emergence happens when system-level properties arise purely from the interactions among the parts. You absolutely cannot understand these properties by just staring at the parts in isolation. Things like safety, resilience, interoperability, they don't live inside a single component. They emerge from how those components talk to each other. And trust me, when those interactions aren't managed properly, the stakes are incredibly high. To really visualize this, think about an everyday situation we've all been trapped in: traffic congestion. Traffic doesn't happen because one car is broken. Traffic emerges from hundreds of drivers making individually reasonable, completely logical route choices. Every single part of that system is working exactly as designed, yet the system-level outcome is a frustrating bumper-to-bumper standstill. That right there is emergence. It's the ultimate proof that you can't understand the behavior of the whole system just by validating the behavior of its individual parts. When we ignore emergence, we walk right into something called the unintended consequences cascade. And it almost always starts with good intentions. Say you optimize a single component to save on cost. Makes sense, right? But without even realizing it, that local optimization strips away redundancy, which decreases your whole system resilience. Then, out of nowhere, a minor shock hits, and those hidden dependencies trigger a massive systemic failure. You solved a local problem, sure, but you just shifted the burden somewhere else. Systems thinking forces us to pause and ask, not just, will this work, but what else might this change? And we have to be asking that question across the entire dimension of time. If you look at the INCO's systems engineering lifecycle, it becomes pretty clear that engineering isn't just a single, isolated event. It spans from conceiving and defining all the way down the line to retirement and disposal. The decisions you're making today, right now in the conception phase, are drastically shaping the risks, the costs, and the overall value during operation decades later. Systems thinking helps us grasp the fact that early choices literally lock in future realities. Over that life cycle, these systems are anything but static. They behave dynamically. They're driven by feedback loops, delays, and accumulations. Just consider a few scenarios. If you defer maintenance to save a few bucks today, you are actively creating massive future costs down the road. If you rush a short-term schedule recovery during development, you are secretly baking in huge integration risks for later. Or, as time passes, simple demand growth can completely overwhelm the initial capacity of your original design. Systems degrade, they adapt, and they interact over time. We have to train ourselves to look for patterns over the long haul, not just focus on isolated events. All of this really leads us to a pretty profound realization about our roles. True engineering judgment requires sense-making under ambiguity. Now, to be clear, systems thinking isn't some replacement for your technical expertise. You still absolutely need to know the math, the physics, and the code. But systems thinking is the essential capability that ensures you are applying that technical brilliance to the right problem. It gives you the confidence to hold on to uncertainty, to question the boundaries, and to resist that urge to prematurely lock into a solution before you truly understand the wider world it's going to live in. So, I want to leave you with one final thought today. When you're faced with your very next challenge, stop and ask yourself, are you just solving a problem, or do you actually understand the situation? Because in our increasingly complex world, building a system that works on paper, that's really only half the job. Ensuring it survives, adapts, and actually delivers real value in a messy, deeply interconnected world, now that requires systems thinking. Thanks so much for joining me on this explainer, and remember to keep asking those big questions.